So let me continue our studies, and we will continue to study random operators, random linear operators in Hilbert space. Yesterday we have seen that from purposes of studying of stochastic differential equations with partial derivatives, we need to discuss such object as a random semi-group of operators. Since we need the notion of random linear operator, a linear operator in Hilbert space. I always will consider H be a separable real Hilbert space. As we discussed yesterday, it will be natural to say that random operator is a random element in LH, where LH is, as usual, the set of all bounded linear operators on the Hilbert space H equipped with the operator's norm. But in case when L is when H is infinite dimensional, we already have that LH is non-separable. I hope that I mentioned this yesterday, and some of you already solved this not very difficult problem to show that LH is non-separable. This causes problems with some with measurability questions because now Borel sigma field in LH is not countably generated. So this attempt is not very good. And as we mentioned yesterday, there are two ways to fix this problem. The first idea to study not arbitrary random operator, but special random operator. For example, a random Hilbert-Schmidt operator. We will consider it further, but I hope that some of you know the definition. Random Hilbert-Schmidt operator, or random nuclear operators. Nuclear means a finite trace. Operator. In this case, we don't need to consider all our space LH, which is rather complicated, but we just take into account all Hilbert-Smith operators or nuclear operators or something else, which is more uh, simple in the structure and is separate with respect to some appropriate norm, Hilbert-Schmidt norm or nuclear norm or something else. This is the first idea, and we will exploit it. The second idea belongs to Anatoly Vladimirovich Skorokhod. Near 75, and of the previous century. And it was formulated as follows. Forget about operator itself. What we need? We need the action of the operator on the element of H. So consider the family of random elements or some people prefer to say random vectors in H, but no, please don't forget that we have infinitely dimensional space. Is a random element here. For every H, and now we will ask good properties of this AH with respect to H. To hold with probability 1 or improbability. Namely, we will say that A is a strong, this is new word here, a strong random operator in H if the following condition holds. The first one. A H is linear with respect to A. With respect to A. H. It means that, as usual, if we apply our A to linear combination A1, H1 plus A2, H2, then we get the linear combination of answers A, H1 plus A2, H2. A, H2. And we just ask that this equality, as usual, holds with probability 1. I will say almost surely. Yeah? As usual, we always say that two random vectors, two random elements, or whatever random, are equal if they coincide on the set of probability one. Yeah, almost sure. And this equality must to be true for all A2, A1 belonging to R, and H1, H2 belonging to H. Okay, the next property reflects our feeling that A is bounded operator. But as I said, the idea is not to require boundedness in usual sense. We already discussed that it causes some difficulties. But let us require the following. Uh, A is continuous in probability. Namely, if Hn tends to H or tends to zero, of course it is enough, but when n tends to infinity, then then A Hn tends to H in probability to AH when n tends to infinity. That's all. This is a definition of the strong random linear operator. It is linear in the sense of random elements, and it is continuous in probability. Now let us think about examples in order to get some imagination what new what new features we can get from this definition. So let us consider some examples. The first example will be very simple. Suppose that A is deterministic. Deterministic element of LH. So A is a bounded linear operator. Then, of course, A satisfies our definition. Then A is a strong linear operator. Linear operator. Let's go for the next example, which is not so trivial. Suppose that we have a sequence psi n is a sequence of uniformly of random variables uniformly distributed 0, 1. Consider the following operator AH. Take En orthonormal basis in H. You remember H is separable, so such basis exist. Define. Define. For all H small from our Hilbert space, AH will be a sum from n equal 1 to infinity psi n multiply on scalar product ENH, and finally multiply on En. Let us note that in this way we get the random element in H. Why? Because it is trivial if we have a finite sum, but series converge every sure because we have the property that sum from n equal 1 to infinity psi n square, I just counting coordinates, squares of coordinates, en h square is finite, yeah, is finite. And now it is trivial because psi n square is less, is greater or equals than 0, less or equals than 1. So it is trivial to conclude that this series converge. Moreover, we have now that norm of AH is less or equal to the norm of H. Actually, it means that we get the example of bounded linear operator. Yeah, it is bounded. It is expected because in terms of functional analysis now, A is a diagonal operator with the psi n on diagonal as an eigenvalues in our basis en. So I think that I don't need to check its continuity and probability. Due to this relationship, it is trivial. It is trivial. But this example give us some interesting questions. The first question is the following. Okay, we just say that we have some new special definition because we already told that this is a strong random operator. But we consider two examples, and it looks like we have nothing new. Is it true that every strong random operator is bounded? And the answer is no. We have a new object which is much more rich as the set of bounded operators, actually. So let us consider example 3. I will take the same example as the same approach is as in example 2, but put in example 2 the sequence psi n to be a sequence of independent standard Gaussian I insist that we still can define A. A is still uh, properly defined. Properly defined. Namely, for any h which belongs to our Hilbert space H, the series sum from n equal 1 to infinity, psi n, en converge sure in H. Again, to check this, let us check. It is enough to consider the series of squares of coordinates. Here is the coordinates, and we just have to consider a series of its squares. So we have the following. Sum from n equal 1 to infinity. Now here we have psi n square en h square. To be sure that this series is convergent, let us take expectation. I will do this as follows. Since we have a series of non-negative summands, I can change the sum and expectation and get the following. We will have the sum from n equal 1 to infinity. Expectation of psi n square en h square. And since psi n is a standard Gaussian variable, then its expectation of the square is equal to 1. And finally, I will get that it is equal to sum from n equal 1 to infinity en h square, which is just norm of h square. From this point of view, we understand that the initial series converges almost surely. Yes, because if we have that the expectation of some function this function is which is non-negative is finite, it means that the function is finite almost surely. And it means that initial series for our definition of AH converge almost surely. Okay, the linearity is trivial. And now what about continuity? Continuity also is trivial because continuity. Because we have this estimation from above, so one can see that if we consider expectation of the norm AHN minus AH square, then it is the norm of Hn minus h square, which tends to 0 if Hn tends to h, when n tends to infinity. Since then, one can conclude that our operator A is continuous not only in probability, even in square mean. Now we have the following. Hn converges in L2 to AH when n tends to infinity. But where did we use the condition that psi n are independent? No, we don't use it. We did not use it. But now we will. Namely, now let us look, let us consider the following quantity. Step where n greater or equal than 1, absolute value of psi n. I claim that it is plus infinity, almost surely. To check this, one can apply for example, Borel-Cantel lemma. Namely, we know that for arbitrary C, which is greater than 0, the series of such probabilities, sum from n equal 1 to infinity, probability that absolute value of psi n is greater or equal than C, which is exactly due to the condition that all psi n have standard normal distribution, is the sum from n equal 1 to infinity. Probability that psi 1 is greater or equal than C. And of course, because normal distribution has density, which is positive on the all real line, this quantity is greater than 0, then it is plus infinity. Now, since independency of psi n, the random events psi n greater or equal than absolute value greater or equal than c, n is greater or equal than 1, are independent events, and you can conclude from Borel-Cantelli lemma that uh, that probability, hence probability that infinitely often absolute value of psi n is greater than c is 1. Yeah. Now, using obtained relation for the c equal, for example, n capital, where n is natural number, one can get that probability of intersection of such of such let me probability of intersection of such events. Here is n from 1 to infinity. Here we have the events that infinitely often psi n is greater or equal than n capital also is equal to 1, because we have a countable intersection of the events of of probability 1. But if we denote for a moment this event by omega prime, then for every omega, from omega prime, it is evident that sup over n is greater or equal than 1, absolute value of psi n of omega is equal to plus infinity. So we have the following relation, but from the university course of functional analysis, we know that this relation means that diagonal operator with psi n omega n is greater or equal than 1 is unbounded. We know that diagonal operator in the orthonormal basis is bounded if and only if the eigenvalues are bounded. But here we have this relation, which means that we have opposite case. Since then, what we get? We construct very simple operator like this one. This diagonal operator with the in orthogonal basis En with the random eigenvalues psi n. So what happened? What is wrong? The wrong is the following. You see, here we say we said this series converge almost surely, but this almost surely depend on this H and is different for different H, for different elements of our Hilbert space. It means that we cannot find, and we proved it already, we cannot find the set of total probability 1 on which all the series converge for every H. There are no such set because the set of this H is uncountable. So we already knew from the course of probability that sometime the intersection of uncountable sets of probability 1 can have probability 0. Exactly this case happened. Okay, this is the first example of such a new situation. We have a strong linear operator which is not bound. Another one example. Another one example. Another one example is related to integration with respect to inner products. Yesterday we mentioned that if Wt t is less okay greater or equal than 0 is a Wiener process. You remember it is a Gaussian process with stationary independent increment centered and its increment on the interval of the length t has a variance t. Is Wiener process. Then somebody can define the integral. The integral from 0, for example, to 1 f t dwt. And this integral can be defined as the limit of the integral from the step functions for all f which belongs to L201. So we have even not the operator. We have a random linear functional. Yeah. Moreover, it satisfies Korохod it satisfies Korохod definition because we just said yesterday that this integral has a Gaussian distribution. Has a Gaussian distribution with expectation 0 and variance norm f square. From this point of view, everybody understands that this integral is linear, firstly, and secondly, is continuous even in square mean. Yeah, on the space L201. Excuse me. On the space L201. But let us check that it is non-bounded operator. Yeah. For example, consider the very simple function fn t is equal to indicator function of the interval 0 t. 0, excuse me, 0, 1 over n. So the graph of this function is also very simple. It looks like following. Here is interval 0, 1. Here is also 1. And here is 1 over n. This function is equal to 1 here. And then it is equal to 0 here. This is just a function. And even for those of you who are not familiar with eta construction and with all stuff from integration theory, it is clear that for such function, the integral from 0 to 1 fn t dwt is equal w 1 over n minus w0, and simply it is w1 over n. Yes, this is simply integral from the from the following function. Now, suppose that now prove that this is our functional is unbound. Now consider the norm of Fn. It is trivial to see that norm of Fn square is equal 1 over n. Then to check whether our functional is bounded or not, let us consider the following. Let us consider the sup over n, which is greater or equal than 1. And here I must have a ratio of this integral. This is a value of our functional, fnt dwt divided by the norm of our function fn. Yeah. In case we have a bounded functional, the sup must be bounded. But I'm claiming that it is equal to plus infinity, almost surely. Why it happens? The reason is very trivial and is based on the law of iterated logarithm for Wiener process. Let me recall it. A law of iterated logarithm for Wiener process. It looks like this. For now, I will use it for our sequence. The upper limit when n tends to infinity of w1 over n divided by 2 square root of n. Here ln. What does it mean? I will adjust. This is double logarithm. No, excuse me. I did not finish it. So this is and I will explain it just now. It is equal to 1. With probability almost sure. Here the ln is equal simply ln of n. This iteration gave the name to this relationship. Yeah? You see here this function. Yeah. Then our relation mean follows immediately because of this one, yeah, and this. So one can now conclude. One can conclude now that this uh, random functional is a strong random functional, but not the bounded functional, yeah, with probability one. A last example I will give you as an exercise, but we need this example since we will consider random operators which arise in the theory of stochastic flow. So we'll discuss this example detailedly later. But you can check it very easy using the idea of the previous example. Suppose that our space Hilbert space H is a space of square integrable functions defined on 0, 1. Now I will consider a theta, which is a random variable, uniformly distributed, uniformly distributed on 0, 1. Then define the following random function. AH from the function h from our space is equal h of theta. Since theta is uniformly distributed and is random variable, h is measure of function, the composition is also random variable. Moreover, it is evidently linear, and now it is easy to check that expectation of h theta square is just the norm of h in square. So we really have a, random functional, linear functional, yeah? But please check that, oh, excuse me, here I forgot A. Yeah, I forgot A. That expectation of AH, maybe better to put here brackets. So, but please check that A is not bounded functional with probability 1. Probability 1. This is exercise. And now, when we consider this H, maybe one can already understand which problems we will have. Why? Because here we have actually very common situation from the theory of partial differential equation. Why? Let me recall you that when you consider the solution to partial linear differential equation of the first order, you use a characteristic method. And the solution is nothing else than shift of the initial condition along two characteristics. So, what we will get in a random situation, we will get a stochastic flow, maybe some stochastic shift, like this one, and this H will serve as initial condition, and we finally will get such kind of superposition. And we already have seen that it is unbounded operator. You see? So let me emphasize that these examples give us feeling that the notion of the strong random operator is not so artificial. It is not just a pure mathematical idea for some generalization or to make some nice but unuseful construction. No, it arises with necessity in the theory of stochastic partial differential equation, and we will see it in the future. Okay, let's go further. Despite of this news that we have some we have a lot of examples of strong random operators which are not bounded operators. We still can have an interesting examples related to uh, to structure of our operators in some partial cases. For example, consider a self-adjoint self-adjoint uh, random operators. Random operators. Let me recall you the definition. I will consider the following. I will use here the following definition. Definition. The operator A, which is bounded in our space H, is self-adjoint if for all x and y which belong to our space H, we have the following relation. Ax multiply on y, this is scalar product, is equal to x multiply on ai. Let me recall you, we are working in real space, a space on the which is defined above the field of real numbers, not complex numbers. Still, in this case, we also have a good theory about the structure of such operators. Before we will formulate the statement, let us try to recall some example of self-adjoint operators in Hilbert space. I think that we already know some of them. Examples. The one, it is diagonal operator. Again, let En be orthonormal basis. Be orthonormal basis in H and lambda n be a bounded sequence of a real number. Then the operator, which is defined by the then A, which is diagonal of lambda n, and define it as we already discussed. Is self-adjoint. Is moreover, now we can see that for any n we have now we have the following. For any n which is greater or equal than 1, we have that a of en is equal lambda n en. So en are eigenvectors and lambda n are eigenvalues of our operator. And maybe for those of you who remember finite dimensional linear algebra, this situation is already well known. We remember that any self-adjoint or Hermitian matrix in case of complex numbers has a complete set of eigenvectors, orthogonal eigenvectors, and corresponding eigenvalues. So this example realizes the same situation, but in infinitely dimensional space H. It occurs that this is not common situation in infinitely dimensional space. Let me tell you the next example. I will suppose, as before we already did, that now H is equal to the space L2 0, 1, and I will consider as the operator I will consider as the operator the following expression: AH from T is equal to T multiply on H of T. Yeah, this is for T from 0, 1. So what I'm doing, I'm just taking H from the space of square integrated function on 0, 1, multiplied on the free coordinate on T. It is trivial to see that it is bounded operator. It is linear bounded operator. Moreover, A is self-adjoint. Yeah. Now A is self-adjoint. It is also trivial. But what is not trivial, that A has no non-trivial eigenvectors. What I mean non-trivial? There are no function which is not totally equal to 0, such that A of this function is equal to something multiplied on this function, like here. Yeah. has no non-trivial eigen eigen function vectors. Please check it as an exercise. So, how it can be united together to these examples, this very simple and this very unusual from the finite dimensional point of view. It occurs that it can be done using so-called spectral theory for self-adjoint operators. And next time we will see that this spectral theorem still work for random case and continue to study the linear operators, the random linear operators and semi-group obtained from such operators. For today, that's all. Thank you for your attention. Please, if everybody have questions or comments, please ask. I only have a small comment. During a lecture, several times I mentioned that this statement is an exercise. This statement, please check it. I think that it will be very helpful if you will try to do this. And if somebody will have troubles with or difficulties with such small problems, then please ask me tomorrow on our next lecture, and I will be glad to answer everything. For today, that's all. Thank you for your attention, and bye.